This video is going to be looking at the last two core practicals for Unit 6 of Edexcel's A2 Chemistry. We're going to be looking at core practical 15 and 16, which are both organic chemistry. So the first one is looking at the analysis of unknown substances, and it mostly ties in with topic 19, but of course it can tie in with all of our inorganic tests that we've looked at in this entire course. So the experimental objective is to research the tests for ions and organic compounds and be able to successfully test these unknown substances to establish their identity. And there's various links to the specification, and we know that chemical tests can be used to identify either different molecules, or for organic substances they can identify the functional group. Typically though, we would do further analysis such as spectroscopy, just in order to follow up and make sure that we have our structures correct. So when we carry out these tests, we do need a number of different chemicals. We of course need things in order to do our flame tests. We need to test for our halides, sulfates, carbonates. We need our Tollens reagent to test for aldehydes, various different methods that we can use, and you can see that we've got a number of different chemicals as well as apparatus. In terms of safety, of course, wearing eye protection and avoiding skin contact with our reactants or products. If we have a flame test, we just need to be aware of any spitting or hot particles flying off of the wire. And of course, we don't want to have any flammable liquids near our naked flame. So when we're doing an analysis of an unknown substance, we're going to split this into two. So steps 1 to 6 are for our inorganic substances, and steps 7 to 10 are for our organic substances. So for inorganics, we would start off with the cations, and we're looking at flame tests and the sodium hydroxide test. So you have covered both of these at IGCSE and at AS level. We can then identify our anions. So typically we're looking at halides, which can be the silver nitrate test, barium nitrate test for sulfates, or hydrochloric acid to test for carbonates. And again, all of this has been covered at IGCSE and at A level. With regards to the organic substances, we would carry out things like our bromine water test. We would look at Tollens, phthalings, and potassium dichromate. We would also potentially look at hydrochloric acid for testing for carboxylics. We could use Brady's reagent to test for carbonyls. We can use bromine water to test for phenols, various different analysis that we can do. So let's go through some of the results that we would expect to see. So I'm not going to go through everything in great detail, because you can find all of this in the specification or in the practical guide. And that's the practical guide either found on the internet or via Edexcel's website. So we start off with the transition metal compounds. We need to know the different colours of our transition metal compounds, and of course you will cover this in class. And of course looking at very specific differences in the colours, so identifying between the differences between red or pink and red, or red and pink and orange, and of course pale pink. So making sure that we know all of our colours and you can go between each of them. Our flame test, well, we know how to carry this out. So and with regards to Unit 6 paper, it wouldn't be asking about the transitions and about what happens in a flame test. It's how do you physically carry it out. So we know that we need our clean nichrome or platinum wire, mixing in with our solid compound and a few drops of our concentrated hydrochloric acid, and then we're using our roaring Bunsen flame and identifying the colour. And we know all of our flame test colours from IGCSE. Note that for the red, it could be lithium or strontium, so we do need to do additional tests just to verify, is it lithium or is it strontium. So you may wish to look at any decomposition that may be able to, a thermal decomposition that would give you some information. We can also look for transition metals, about what happens when we add sodium hydroxide solutions. So we know that we're going to get precipitates forming, but when we add excess, then sometimes we will see either the precipitate dissolving, like we see for chromium and for zinc, or the precipitate will stay and remain insoluble, and that would be for each of the other metals shown in the video. We can also look at what happens when we add ammonia solution. So we know that we get this precipitate being formed. So remember, we covered this back in topic 17, which is the transition metals. But when we add our excess ammonia, then we can see our dissolving of that to give a solution. So we see that with chromium, with cobalt, with nickel, with copper, and with zinc, making sure that we know all of the different colours of the precipitates as well, of course. The silver nitrate test is one that you would cover back in GCSE, so it tests for the presence of halides, and we know that we can determine whether it is going to be white, cream, or yellow, depending on if it's chloride, bromide, or iodide. And because these colours are quite similar and we need to tell them apart, then we add our aqueous ammonia, either dilute or concentrated, and we can then distinguish between the colours if we can't quite tell by looking at them. We can also use the barium chloride test, and that tests for sulfates, where we get a precipitate of barium sulfate being formed, and even when we add the addition of hydrochloric acid, it does not dissolve. So again, these are ones that we've seen back in GCSE. There's also concentrated sulfuric acid to test for the halide ion, where we get our products of our redox reactions. So these must be carried out, of course, in small scale, and we have to have them in a fume cupboard because these are toxic. So we can see if it's chloride, we would get steamy fumes. Bromide, we get steamy fumes and the brown vapour from our bromine. If it is iodide, we get steamy fumes, purple vapour, a black solid coming from the iodine, and a yellow solid for the sulphur. Note that the products that are in brackets, these are colourless, so we can't see those ones. We can also identify the halides using displacement reactions. Of course, the reactivity is going to decrease as we go down the group. So a more reactive halide is going to displace a less reactive halide. So we would see something, for example, like chloride chlorine displacing something like iodide. Okay, whereas we would not see the iodine displacing chloride. So we have to look at the reactivity there. And we can add our organic solvent, such as hexane or cyclohexane, and we get the dissolving in the layer and the organic layer, so we can see the colour nice and easily. We can look at heat and what happens when we decompose some of these compounds. So we would be looking at the thermal decomposition and looking to identify either carbon dioxide, oxygen, or oxygen and nitrogen dioxide, and that would tell us what carbonate or nitrate we potentially have. Moving on to the organic test, well, the first thing that we can do for any organic substance is we can ignite it or have it undergo combustion. If it is a particularly smoky flame, that tends to be incomplete combustion, and that is caused by things like unsaturated aliphatics or aromatics. If it burns with a clean flame, we're seeing more complete combustion, so that's our saturated, and if we have no residue, we have low mass compounds. Of course, for our organic test, we can also be identifying the functional group that is present. So key ones would be for our alkene or phenol using our bromine water. We can test for any sort of oxidation for a primary, secondary alcohol or an aldehyde using our potassium dichromate. We can use again our silver nitrate to determine what halogenoalkane we have. Phosphorus chloride, phosphorus 5 chloride or PCl5, is used to identify OH groups. We have Brady's reagent for the carbonyl. Of course, our feelings and our tollens will tell us if we have an aldehyde because we get that further oxidation to our carboxylic acid. We have our iodine reaction, which would give us our pale yellow precipitate, or of course we can form an ester with our carboxylic acid. So let's put these reactions to the test and let's have a look and see what knowledge that we have. So this is from the October 2019 paper. There are two different questions, and it is going to be, first of all, looking at the inorganic and then looking at the organic. So a pale green crystalline solid contains 2 cations and 1 anion. So we're going to be looking at what is in each of these. So for when A is warmed with aqueous sodium hydroxide, a gas is given off that turns damp red litmus paper blue. So that must mean that we have an alkaline gas. So by name or by formula, we are forming ammonia gas. Remember, if you give both the name and the formula, both of them have to be correct. So you can give one or the other here if you're not 100% sure. But usually for an A2 level student, you should know the formula for ammonia. We can then determine, well, if we give off ammonia gas, what cation do we have? And the cation is ammonium, which is NH4. And remembering that we have to have the plus as well. A can then be dissolved in distilled water to form a very pale green solution, and it reacts with sodium hydroxide to form a green precipitate, which will then turn into a brown solid standing on air, which is C. So if we go back to B where we form this green precipitate, well again this is somewhat from IGCSE, we know that we must be forming iron 2+, because we're forming an iron hydroxide precipitate. If it was iron 3, then it would be a brown precipitate. So identifying the name or formula for the brown solid, well, I've just given you the answer there, that when we leave this green precipitate to become brown, we must be changing from iron 2 to iron 3. So we are going to form iron 3 hydroxide. Again, name or formula, and if you give both, they both have to be correct. So B, so this is our green precipitate that we have formed, will give a white precipitate when aqueous barium chloride acidified with dilute hydrochloric acid is added. So this is asking what is the barium chloride test for. This must be for a sulfate anion. And again, if you give the formula or you give the name, if we give the name, you need to make sure that you have the correct oxidation number as well, which is 6. So then suggest a formula for solid A. So we know that we're going to be containing NH4 plus, we're going to have Fe2 plus, and we're going to have SO2 minus. Now overall this compound has to be negative, it has to be neutral. So at the moment we have 3 positives and 2 negatives, so that doesn't quite work out. So we're going to say that we must be having 2 sulfates, which gives us an overall charge of 4 minus. We can then have 1 iron and 2 ammoniums. So let's then put that into our formula, where we have NH4 2, 1 iron, and 2 sulfates, giving me a charge of 4 minus, 2 plus, and 2 plus, which gives us a 4 plus. So we're balancing out here. A sample of 0.025 moles of solid A with a mass of 9.8 is heated to remove this water of crystallization that we have, and it leaves 0.025 moles of the anhydrous solid, which is 7.1 grams. Calculate the number of moles of water of crystallization that was combined with 1 mole of our solid. Okay, it's only for 2 marks, and there are 2 different ways that you can do this. I'm going to show you the quickest way, but you can also do this by working out the molar masses. But the best way to do it is work out the mass of water, which is 9.80 minus 7.10, which gives you 2.70 grams. Then work out how many moles that is. So 2.70 divided by 18 is 0.15 moles. We're then going to compare the number of moles of water to the number of moles of solid, and we do that by dividing. which gives us 0.15 over 0.025, which gives you an answer of 6 moles. So we had 6 moles of water in our water of crystallization here. So moving on to question 2, this is our organic chemical test. So what W is a white solid that has C9H8O2. And a series of tests is carried out to determine the different functional groups that are present. So first of all, we ignite a sample of it and we get a very smoky flame. That tells us that probably we're going to have an aromatic compound. We could also have an alkene, but of course that's given to you in the question, but it would be an alkene or an aromatic. We then add some bromine water and we shake it and it turns into a colourless solution. So this is providing us with the proof that we have an alkene or a carbon-to-carbon double bond group. Remember, benzene does not react with bromine water in order to be decolorized, so please do not give that as an answer. We can heat W until it melts and then we add phosphorus 5 chloride and that gives us steamy fumes. So that tells us that we must be containing an OH group. And then heat W until it melts and then add a solid that we have to fill in and we get bubbles of carbon dioxide. So the solid that we're going to be adding is most likely going to be sodium carbonate. We can also use potassium carbonate, sodium hydrogen carbonate, or potassium hydrogen carbonate. Any one of those would be acceptable. And that tells us that we have a carboxylic acid group. We then want to complete the table, which gives us the information about the mass spectrum. So the peak at Me we don't know. It gives us a peak of C6H5+, so that's telling us that there is a benzene ring here, and that peak occurs at, well, we just have to add up the mass of those, and that's going to give us at 77. The peak occurring at 103 is due to an ion with the formula of, well, we have to determine how many additional hydrogens or carbons that we need to add in there, and we figure out what mass that would be, and that would give us C8H7+. So it's the addition of 2 carbons and 2 hydrogens. So the low resolution proton NMR gives 4 peaks with a relative area of 1 and 2 peaks with a relative area of 2. How many proton environments do we have? Well, remember, our proton environments are how many peaks we have, so we have 6 proton environments. And what can be deduced from the relative peak areas? Well, remember, the peak tells us how many protons there are, so we have 4 environments with 1 proton, and we have 2 environments with 2 protons. And now D exists as 2 geometric isomers, so we know that there's going to have to be a double bond in here. And we want to use all of this information to deduce the structure of at least one isomer. So just a reminder, we had the formula of C9H8O2. We know we're going to have a benzene ring. So let's add that in first of all. So that takes away C6H5. We must have at least 3 more carbons. And we know that we must also have a double bond. So that's given us 6 carbons in the benzene ring plus 7, 8, 9. For hydrogens, it gives us C5 and then 1 hydrogen on the first carbon of the double bond. So that gives us 6. And 1 carbon of the second carbon, 1 hydrogen on the second carbon of the double bond, which gives us 7. So we now need to add 2 oxygens and a hydrogen, but if we go back to our information, we know that it contains a carboxylic acid group, so this must become our carboxylic acid group here. And you can either draw the E or the Z isomer, both of them would give you the same answer. So you can check everything on the mark scheme if you wish, if you've been working on these questions on your own. And now let's move on to the last core practical, which is the preparation of aspirin, which is in topic 20, organic synthesis. So we want to be able to perform and explain the reactions of acid anhydrides and how we synthesize aspirin from 2-hydroxybenzoic acid. So an acid anhydride is a compound that has 2 acyl groups bonded to the same oxygen atom. And I'll show you an example of what the structure looks like in just a few minutes. Aspirin is formed in the presence of a catalyst such as sulfuric acid or phosphoric acid. So what we're going to need here is our acid anhydride, in this case ethanoic. We're going to be using 2-hydroxybenzoic acid because that's our starting reagent, and of course we need our catalyst. We're also going to be using distilled water, ethanol and ice, plus a number of different laboratory equipment such as measuring cylinders, pear-shaped flasks and Bunsen burners, and of course our vacuum suction. So for safety, of course, wearing eye protection and also wearing gloves. Ethanol is flammable, so make sure it's not near an open flame, and ideally we should be using a fume cupboard for this if we can't ventilate the room properly. So the first thing that we have to do is actually prepare the aspirin. So we weigh out 2 grams of our acid and we put it into a pear-shaped flask and we suspend that in a beaker of water. We add our acid anhydride to the flask as well as our catalyst, and then we put a condenser onto it. We then, in a well-ventilated room, use a Bunsen burner to carefully warm the mixture whilst swirling in order to dissolve the solid. After 10 minutes, we want to remove the flask from the hot water bath. We add 10 centimetres cubed of crushed ice and some distilled water in order to break down any unreacted ethanoic anhydride. And then we're going to stand the flask in a beaker of water until precipitation starts, and we're going to filter it using a Buchner funnel and the minimum amount of ice water. So now we're going to look at the recrystallization part of the process. So we're going to set up a water bath ready with boiling water. We put the crystals into a boiling tube and then we add some water and put the tube into the water bath, and that's allowing us to dissolve the crystals in the minimum volume of hot water. Very important that we know it's the minimum volume. If there are any insoluble impurities, then we can carry that out with fast filtration. So that is just a simple filtration, and making sure that we have our preheated glassware because we want this to be a hot filtration. Then we allow the solution to cool, and we do this slowly at first, and then we'll use an ice bath if necessary until we get crystals reappearing. So we had crystals at the start, we've dissolved them in the minimum volume, carried out the fast filtration to remove those insoluble impurities, and then we want the crystals to reappear. We're then going to filter the crystals under suction using our Buchner funnel, and then we want to wash with a small amount of cold water just to get rid of any soluble impurities. And then we allow the crystals to part dry between the filter paper and then put them in a nice warm oven to thoroughly dry them and get rid of any water that may be there. And then we want to check its purity, so we do that by measuring the melting point and then checking the yield. So this is what the whole process looks like plus our equation. So we have our starting materials, this being our acid anhydride, and that would give us aspirin and also ethanoic acid as a side product. So we carry out, first of all, heating under reflux with our condenser. We then do a recrystallization, and then we do a melting point determination. That is the 3 steps, and these are 3 steps that you could be asked about in your Unit 6 exam. Particularly, the one that I would focus on is recrystallization. That tends to come up a lot in past papers. So just an example of what this may look like. Well, our starting material has a molar mass of 138 grams per mole, and aspirin is 180. If we start with 2 grams, we should, in theory, once we do our calculation from balanced equation, from 2 grams we should make 2.61 grams of aspirin, because we have 0.0145 moles, and of course they're in a 1-to-1 ratio. Now that is our theoretical yield. Our actual yield is a bit lower than that. We're saying that our actual yield is about 2.25 grams. So once we figure that out, we can determine the percentage yield, which is 86.2%. It's very unusual to get 100% yield from a reaction like this. We do always have a slightly lower yield just due to the conditions. And when we do our melting point determination, what we should find is that the melting point is 136. So let's have a look at a past paper question just to finish off. This is from the October 2018 paper, and it outlines the procedure of methyl 3-nitrobenzoate by doing the nitration of methyl benzoate. So it's not exactly the same as what we were just looking at, but the steps of how we do this are very similar. So part A is suggesting why we use an ice-water mixture rather than only using ice cubes. Well, if we think about the purpose of it is allowing us to try and cool it, so we want to have as much contact as possible. So if we only use ice cubes, we have less contact for cooling, because you'll only get cooling on the surface of the ice cubes. So the equation for the nitration of methyl benzoate is as shown here, and we want to give a possible isomeric product of this reaction. Now, I'm going to not have any space in here to do this, so I'm going to show you what the isomer should look like here. Well, we have our NO2 group going on to this carbon, so I could either have my NO2 group going here, or I could have, if I redraw it, I could have that, and I could have my NO2 group going on to carbon number 4. 2 possible positions there. And for part 2, give the structure of a possible aromatic product if this reaction rises above 10. Well, if that happens, then we're going to get additional substitution. So instead of getting our mono-substituted product, we would probably get a di or tri-substituted product. So I'm going to draw up the answer to part 2 on this one. So you could get something like that, or you could also get something like that. Any one of those would be accepted. Part C is looking at the diagram of the reduced pressure filtration apparatus, and the student's diagram has 2 mistakes. Now there are actually 3 modifications that we can make here. We can pick any 2 of them. So the first one is that in our Buchner funnel, we should be showing that there are holes So rather than just this solid black line, we should be showing that there are holes within this. The second part is to do with this part here. There are 2 ways that we can answer this. We can either have this tube going to a tap and then have a second tube going to the sink, or we can change this. So we want to use a vacuum pump instead of the tap. And then the third part is the filter paper at the sides here. The filter paper should be trimmed. We don't want the filter paper going up the side of the Buchner funnel like that. We want it to be sitting absolutely flat. Part D is then looking at recrystallization. As I said earlier, this does come up all the time in exams, and we want to describe the steps of how we do this in order to remove any soluble impurities and produce a pure dry sample. So there are 4 parts to this. The first part is to dissolve the crystals in the minimum amount of solvent. Minimum amount of hot solvent. The second part is then to cool in an ice bath. We then filter using a vacuum filtration. And you can specify using a Buchner funnel or a Hirsch funnel, it doesn't really matter, and that's in order to remove our soluble impurities. And then the fourth part is to dry the crystals, and there are various ways that we can do that. We're going to say in a warm oven. Note that it is not a hot oven because that would then melt our crystals. So we want to calculate the mass of methyl 3-nitrobenzoate produced from 2 grams if the percentage yield is 73. So if we just go back, we can see that we're going to have a 1-to-1 ratio. So I can work out my number of moles is 2 grams divided by my molar mass is 136, which gives you 0.0147. It is a 1-to-1 ratio. Therefore, we have 0.0147 moles of the product. So my mass is going to be 0.0147 multiplied by 181 to give me my theoretical, which is 2.66 grams. And then my actual is going to be 73% times 2.66, which gives me a mass of 1.94 grams. And then part F, the last question, is looking at the purity. So the purity can be tested by determining the melting point. The literature value for methyl 3-nitrobenzoate is between 78 and 80. If this was an impure substance, or if there were impurities present, how would this affect the melting temperature? Very simply, you would have a wider range of a melting temperature, or it would melt at a lower temperature. Either one of those would be accepted. So you can have a check at the mark schemes should you wish to have a look at the answers for the ones that if you've been working through them yourself. That's everything for Core Practicals 15 and 16, and that is therefore everything for Unit 6 of A2 Chemistry. I hope this video has been useful, and if you do have any comments or questions, please feel free to post below, and we hope to see you back on the channel for any future revision.